Hello, and welcome to the May edition of the Agile Austin Product and AI SIG. Today we have Tristan Slominski here to talk to us about AGI, um, artificial, boy, artificial. I'm blanking already, even my recording thing. AJ is not what you think it is. So he's going to be talking about his work. And before we get there, let's just talk briefly about Agile Austin. Here's our mission. Although we are in Austin, many of our participants today are all over the country, the United States, and sometimes all over the world. This is the board. Max Akizi is our president, and oftentimes you might see Ben Rogers here. We do sponsorships. We don't need a ton of money, but things like Zoom and other things that we do helps if we do have sponsors. You can be a member. It's $35 a year. I am a member myself. Gives you access to certain benefits, but all of our events, except the Keep Austin Agile conference that just happened last month, are free of charge. We also have six meetups that are going on a regular, continuous basis. We have the Product and AI SIG down there on the bottom left, but you can see there's other special interest groups that we have: coaching, skill, book club. Ed Horvath leads, and he's here today. Lean Kanban and leaders. We have some sponsors that we thank every single time. Agile Velocity is our platinum sponsor, and ResumeX is our gold sponsor. And we have a relatively new sponsor, Admiloria Coaching. If you have any questions about those sponsors or sponsorship in general, just let Vishal or I know. One of the benefits we have for members is a scholarship. And if you do pay that $35 a year, then you can apply to get a professional development membership. And one of our sponsors, Agile Velocity, offers 15% off of public workshops. There's a QR code there. If you missed it, please feel free to come back and ask me for it. Everything we do here is volunteer. I know it's hard to imagine with such a professional setup like I'm doing right now, but we all are volunteers. We're citizen, I don't know, soldiers, elected, non-elected officials that just participate. We make the magic happen here, which means that you can too. Couple of those sponsors, just to talk about this SIG right here, both Vishal and I are responsible for this SIG. We serve the community by shepherding this through. Both Vishal and I started with Agile Austin back in, it's hard to believe, almost 20 years ago, 2007. And then we've got our mission statement up there on the left. We talk about product and AI. And about that order, sometimes we lean a little bit heavy on product, sometimes a little bit heavy on AI, or in this case, artificial general intelligence, AGI. Next month, we've got Ravi Verma, who's going to be talking straight from Keep Agile Austin last month, Unlocking Product Management with Generative AI. We are looking for speakers for July and August. And there it is. Could this be you? What have you learned? That's what a talk can be. It's as simple as that. But today, we have Tristan. I think Tristan and I met many years ago in Austin, has been a long time contributor to the Agile Austin community, and really through participation and even in meetings and raising hands saying, I disagree with that. Has always good, just amazing perspectives to offer. And I was just thrilled that he was part of this the Thousand Brains system. So he is as you can sort of read there, veteran and former aviator. I think that's probably how we met, Tristan, after you came out of like your service. Thank you for that. Worked in small startups in Austin and Bazaarvoice, which was one of the big, which was a small startup and it became really big. And now he is actually, I think, is it the first developer at Thousand Brain Systems, Tristan? Is that or
Yeah,
near?
I was hired to start working on the open source software. So
Yeah. So super excited to have Tristan here talking about that. Um, and it's an open source nonprofit project, sort of reverse engineering the neocortex to revolutionize AI. And there's a couple of these core principles, and there's a great book if you read it. It's called Thousand Brains, right, Tristan?
Correct. Thousand
Yeah,
Brains.
Thousand Brains by the one of the co-founder uh, of Palm Computing, if you had that back in the day. He also happens to be a brilliant neuroscientist and computer scientist too, go figure. And he wrote this amazing book and had this different perspective on how to do artificial general intelligence. Um, so Tristan's going to talk about some of those principles and how it's, sort of intelligence is derived from sensorimotor learning, which is like your brain and how you do things and explore the world and how the brain works there. And then it's going to talk about sort of like, because this isn't, we went back and forth, Tristan and I. It's like, well, maybe it's a little bit too advanced. It's not enough practical advice, but he said, well, there's some practical things now. And so there's enough practicality so you could take this and, start thinking about, start using it or start, sort of positioning yourself in product and your AI usage. So with that, I'm going to stop sharing and give it over to Tristan.
Thank you. Let me share. Here we go. And you should all now see my
Looks
slide
great.
screen. Okay, excellent. All right, so thank you for that. Hello and welcome. My name is Tristan Slominski. I am a principal engineer at the Thousand Brains project. And today I am going to share a future history of how the Thousand Brains project reverse engineered the neocortex and developed sensory motor intelligence. So who am I? Why are you hearing from me? I am an engineer on the project, which means that amongst other internal responsibilities, I work on the software of the Thousand Brains system. My focus is on enabling our researchers and or on turning research into working software. However, I am not a researcher. So I want to highlight my not a researcher status to point out that while I've personally learned a lot of neuroscience by being on the project, I am likely not the best person to answer all of your neuroscience questions that might come up. So as the saying goes, predictions are difficult, especially those about the future. And also, I personally do not like making predictions. However, since this is a product and AI meetup, I feel that some discussion of the future is inevitable. So I imagine that all of you have thought about how the future of AI will turn out at some point. What I would like to do is present to you an alternative to the prevailing view. And this alternative offers different capabilities both today and paints I think, a very different picture of the future. So this presentation will have two parts. First, I will tell you a future history of artificial general intelligence, or AGI. By future history, what I mean is we will all imagine that we are at some point in the future now. AGI is all around us. And what we're going to do is just look back from that future spot and kind of go backwards all the way to today and figure out how we got to this amazing future where AGI is all around us. So we're going to kind of go backwards through time. Why we're doing that is I want to try that. I want to do something different. But what I will do for relevance to product is I will highlight our project milestones. So these are the inflection points that you may want to pay attention to as a product person. So each of these milestones opens up new opportunities and markets. The second, once we come back all the way to the present, then I will share with you the current capabilities of what a Thousand Brain system can do. All right, so with that, let's get started. So we'll begin at the end, where the unimaginable has become the ordinary, because to understand the future we live in, we must first understand how we built it. So today, what people used to call AGI, or artificial general intelligence, is ubiquitous for a price. The transition point came quickly after the achievement of the three latest Thousand Brain Systems milestones: theory of mind, multi-agent systems, and abstraction. These were necessary to enable cooperation between AGI and people, as well as between AGIs themselves. Representation of abstract concepts didn't happen earlier because, as it turned out, bootstrapping abstraction from grounded real-world experience was more effective than the other way around. This is why for the Thousand Brain Systems, language acquisition came last. This is also why it happened practically overnight. Now, thanks to these milestones, robots are finally expanding into every inhospitable and hazardous niche that humans find valuable and where autonomy and cooperation is essential. They are our first responders. When disaster strikes, it's an AGI that arrives first. Not a hero in uniform, but a machine built to rescue. They construct, maintain, and operate habitats, power stations, and manufacturing facilities on our frontier, on asteroids, Mars, Venus, and in deep space. AGI operates any significant logistics network, from off-world and international shipping to last-mile delivery. AGI tutors and teachers provide customized education. AGI researchers plan and conduct experiments. They develop new mathematics. They cure disease and develop vaccines. And because we developed AGI based on the human neocortex, not only do we understand how AGI works, but we also understand how human intelligence works. So AGI psychologists are becoming viable for humans and AGIs. There is ongoing research into neuromorphic neocortex prosthesis modules to mitigate brain damage from trauma or disease. Effective treatments for mental disorders are available. AGI has grounded language understanding. Detecting ads, propaganda, or misinformation is easier than ever. Close to optimal protocols accelerate our acquisition, transfer, and retention of expertise. Government, commercial, and other organizations are modeled after cooperating multi-agent intelligence. This is now state of the art. So, thanks to these three milestones, that is our world today. But to achieve these milestones, the Thousand Brain Systems had to gather grounded real-world experience. How did they do it? What enabled gathering grounded real-world experience was the previous milestone of world manipulation. World manipulation was the ability of Thousand Brain Systems to shift from observing the world to changing it. Before this milestone, Thousand Brain Systems were already capable of sensory movement. After all, that is what made them so effective at observation. But the ability to go from getting a better view to moving and affecting things with purpose was a real breakthrough. Once Thousand Brain Systems were capable of world manipulation, the symbiotic relationship with neuromorphic hardware paved the way for robotics applications to take off in a big way. Robots mined the earth. Robots farmed. Robots constructed, maintained, and operated habitats, power stations, and manufacturing facilities as far as the moon. Robots provided healthcare and performed surgery. But most importantly, a robot was now able to clean your house and do your laundry. All of this became possible thanks to rapid advances in hardware. The Thousand Brain System approach enabled neuromorphic hardware improvements, which in turn fine-tuned the Thousand Brain Systems techniques, which in turn drove demand for improved neuromorphic hardware, and so on in a virtuous cycle. The hardware improvements were known and anticipated long before, but their full potential was unrealized. Just as neural networks, long known before the 2020s, only proved transformative after the scaling of compute during that decade, it was the Thousand Brain Systems architecture that finally unlocked the neuromorphic computing potential. So, world manipulation, combined with neuromorphic hardware, enabled vast robotics deployment, which gathered grounded real-world understanding. This then enabled the abstraction, multi-agent systems, and theory of mind milestones. Now, in order to learn world manipulation in the first place, the thousand brain systems needed to be capable of modeling object behaviors and world dynamics. These milestones gave the thousand brain systems the ability to understand change. It turned out, perhaps surprisingly, that a singular mechanism for understanding change enabled everything that followed. Once thousand brain systems understood change, they could interact with the world by being embedded in or collaborating with previously existing technologies. In well-defined domains, thousand brain systems were embedded in self-driving cars and other autonomous transportation. They were widely adopted as universal online pattern recognizers. If you needed an ultrasound of your heart, a thousand brain system could walk you through the process and diagnose any issues, minimal training required. What drove the embedding of thousand brain systems was the big benefit of online learning from little data. In agriculture, thousand brain system could rapidly learn the local ecology and identify weeds, disease, and pests. Thousand brain systems became essential for cybersecurity, monitoring, and detection. All of these online pattern recognition tasks became accessible due to object behavior and world dynamics modeling. So again, modeling object behaviors and world dynamics enabled thousand brain systems to understand change. This led to thousand brain systems being embedded in existing technologies. That embedding provided the groundwork for world manipulation. World manipulation and neuromorphic hardware led to a vast deployment of robotics, and this provided grounded real-world experience on which abstraction, multi-agent systems, and theory of mind were built. Now, you might think that without understanding change, there's not much a system can do. However, there were already many thousand brain systems deployments by this point. Most of what we perceive in the world, we perceive as composed of parts. One way to think about this is that world has unfathomable variety. Yet you and I are able to make sense of it by reducing that variety into things made of other things. We think that cars have doors, wheels, and windows. We think that people have limbs, thoughts, and behaviors. We think that ideas have parts, sizes, value. The ability to perceive compositional objects provided a mechanism for the thousand brain systems to reduce variety and begin to understand the world. With compositional objects, thousand brain systems were capable of complex object recognition and mapping. Even without behaviors and dynamics, there is much complexity in a static world, and thousand brain systems readily tackled this complexity. All sorts of medical imaging and remote sensing was diagnosable by the thousand brain systems. The thousand brain systems worked alongside operators by directing them where to move the sensors to facilitate tasks. Due to their online learning from little data, thousand brain systems were reliable processors for all types of remote sensing. They could detect abnormalities without needing to train on examples of them. They were rapidly integrated into existing systems and infrastructure to provide universal object and scene recognition. They mapped disaster zones. They rapidly understood interiors of rooms, warehouses, factories, and all spaces. Thousand brain systems structured knowledge representation was already hinting at the future benefits of reality-grounded understanding. All this rapid growth in capability and application just from compositional objects milestone. So the ability to perceive compositional objects, provided a mechanism for the thousand brain systems to reduce variety and begin to understand the world. This enabled thousand brain systems to perform complex recognition and mapping. Then modeling object behaviors and world dynamics enabled thousand brain systems to understand change. This led to thousand brain systems being embedded in existing technologies. That embedding provided the groundwork for world manipulation. World manipulation and neuromorphic hardware led to a vast deployment of robotics. And then this provided the grounded real-world experience on which abstraction, multi-agent systems, and theory of mind were built. But even before compositional objects and the variety reduction, thousand brain systems were showing promise regarding their need for data. It all started with object and pose recognition. The ability to move the sensor in order to gather information in context proved to be a paradigm shift and something that other approaches were unable to exploit. Ultimately, the sensorimotor paradigm is what let thousand brain systems generate their own training data in context, fit for purpose, and only the amount necessary. What could thousand brain systems do with object and pose recognition? They could do continual learning with little data. The first thousand brain system, Monty, was able to reliably recognize objects in different lighting conditions, different textures, and occlusions. This turned out to be valuable for recycling and for manufacturing applications. At the time, there were other technologies capable of addressing some aspects of this problem. At first, Monty proved useful in small operations where there was not a lot of data to train contemporary AI solutions. But eventually, with its multimodal capabilities, Monty proved to be a more economical, scalable, and adaptable solution in large operations as well. So objects and pose recognition, alongside continual learning from little data, provided early wins for Monty. Later on, the ability to perceive compositional objects provided a mechanism for the thousand brain systems to reduce variety and begin to understand the world. This led to complex recognition and mapping. Then modeling objects' behaviors and world dynamics enabled thousand brain systems to understand change. This led thousand brain systems being embedded in existing technologies. That embedding provided groundwork for world manipulation. World manipulation and neuromorphic hardware led to a vast deployment of robotics, and that provided the grounded real-world experience for abstraction, multi-agent systems, and theory of mind. Back then, it was not at all obvious that sensory motor learning would be the groundbreaking idea on which we would build the world we have today. In the end, as one of the historians later remarked, all we needed to do was to teach the machines to move, and in their movement, they learned to think. This concludes the future portion of the presentation, and I will now switch gears to talk about the capabilities of the system today. What I want to share with you is our general sensory motor approach to intelligence. Sketch out some implementation details so you can see that this is working, and thus provide some evidence that the path towards the future I just outlined really does exist. So in March 2021, Jeff Hawkins published his latest book, Thousand Brains Theory, a New Theory of Intelligence, in which he articulates a sensory motor theory of intelligence. At a high level, the thousand brains theory is a theory of how the human neocortex works. And the Thousand Brains Project is our nonprofit organization focused on advancing and implementing the Thousand Brains theory. So what is the Thousand Brains Project? It is a nonprofit research company. It is an open source project, MIT licensed. It's building a new type of AI that is based on principles of the human neocortex, made for sensory motor applications, and it is a general system with all the capabilities of the neocortex. In an attempt to highlight what brains are good at, here are some very high-level correlations. We have our calculators and computers that are good at numerical operations. We have deep learning LLMs with their large number of applications. And then we have the Thousand Brains project for sensory motor learning and action. Note that sensory motor does not need to be physically embodied, like in a body or a robot. So while it is a great fit for robotics, an analogy of sensory motor can be applied to virtual systems and abstract spaces as well. For example, like navigating the internet. We call an implementation of the thousand brains theory a thousand brains system. So what does a thousand brain system look like? It is a system built on a few key principles that we're going to go over next. So first, we have sensory motor learning. Learning in every intelligent species is fundamentally a sensory motor process. So a thousand brain system will be able to ingest a continuous stream of self-generated sensory and motor information, like a child experiencing an object when playing with a new toy, exploring it with all its senses and building a model of the object. The system actively interacts with the environment to obtain information it needs to learn or to perform a certain task. Active learning makes the system efficient and allows it to quickly adapt to new inputs. Next, we have reference frames. As the neocortex learns models of the world, how do objects look and feel like, where are they, and how do they behave, these models are structured by reference frames. Each reference frame stores where things are relative to each other. They're not just a bag of features. These structured representations make it possible to perform necessary tasks for survival quickly, such as path integration and planning. Next, modularity. This is where the name of the thousand brains comes from. The neocortex is remarkably similar everywhere. It is composed of general, repeatable functional units called cortical columns that learn models determined by their input. Each cortical column implements a general purpose algorithm for modeling sensory motor data, allowing for local, fast, and associative learning. Each cortical column can model complete objects. Each cortical column can know about many objects, and no column can know all objects. It is worth highlighting how small an input into a cortical column is. To conceptualize this a bit, imagine looking at a world through a straw. For example, in the visual system, the right and left visual fields are separated. In the eye, on the retina, there are blood vessels everywhere. The optic nerves makes a big hole we don't notice, and eventually all the input ends up in V1, the striate cortex. The neurons in the V1 area have small receptive fields. So when looking at a screen, a V1 neuron sees less than 1 centimeter. That is the input into a cortical column. Yet we see things. The combination of small receptive field and the saccades occurring 3 to 4 times per second allow each cortical column to recognize things, even though it is like looking at a world through a straw. All of these cortical columns need to communicate with each other and with the motor system. These communications must contain certain essential information for the system and the brain to work. So we represent this communication using the cortical messaging protocol. All of these key pieces put together, sensory motor learning, reference frames, modularity, and cortical messaging protocol, guide the project's research direction and our implementation choices. What is important to highlight here is that we do not intend to build exact biological replicas. The systems we build, as long as they abide by these principles, will reproduce the functionality of the neocortex. So, following these principles, what sort of system are we building? Here's a conceptual architecture overview so you can identify the system components involved and how they interact together. In the diagram, the square icons represent the learning modules. The rounded at the top icons represent sensor modules, and the trapezoid represents the motor system. A learning module is our abstraction and implementation of a cortical column that I just talked about. A sensor module is our abstraction and implementation of sensory data being converted into CMP, the cortical messaging protocol. The motor system is our abstraction and implementation of the motor system. So the solid lines on this diagram depict communication via that cortical messaging protocol, CMP. And let's highlight a few important elements of CMP that are depicted here. So a pose is what we call the location and orientation in a common reference frame. Features are what you may usually consider a feature, like color, curvature, luminosity, etc. And then there are other auxiliary parts like confidence, sender ID, etc. These are the solid arrows in the diagram. The dashed arrows represent specific communication, sensor-specific communication protocols that are not CMP. So let's say the eye sensor on the diagram here made an observation. It will send this observation to the sensor module via this dashed specific sensor-specific communication protocol, like a signal going from your eye to the brain. The sensor module sends the observed state to the learning module via the CMP. The learning module then sends the hypothesized state to other learning modules in the hierarchy via the CMP. And then also the learning modules vote on possible states with other peer learning modules via the CMP. And then lastly, the learning module sends a goal state to the motor system via CMP. Again, this is intended to illustrate the main system components, but we can arrange these in multiple ways. So for example, we can link together multiple senses in a multi-model configuration so that these learning modules connected to LiDAR and vision can collaborate on what they are sensing. By introducing hierarchy, we can model compositional objects. In this setup, one learning module's hypothesized state output will become an input for a learning module higher in the hierarchy. And we can extend and scale these arrangements. So here we have 4 touch modules and 4 vision modules arranged to vote together in a hierarchy under another set of higher level modules. Not depicted, but also possible are skip connections, hierarchical separations, and any other setups you can think of. So now let's go over sensor modules, and I'll explain learning modules next. Each sensor module sees a small part of the object and can move. So from the 2 illustrations here, the illustration on the right is what the sensor module actually sees. The viewfinder on the left is there just for you to give you the context and to help orient you as to what the sensor module is doing. But the sensor module itself only sees the patch on the right. This is the view of the world through a straw. As mentioned before, the sensor module turns raw data to the cortical messaging protocol. And for example, like an RGBD camera sensor, red, green, blue depth, will turn a patch into a point cloud of XYZ coordinates, and it will extract those pose and features that I talked about and send those via CMP. Now, let's talk a little bit about learning modules. Again, learning modules are based on cortical columns and model the incoming stream of poses and features using reference frames. This is the sensory-motor integration. For context, depicted here on the right here is a schema of a cortical column. So the height of a cortical column is around 2.5 millimeters, and surface of it is about 1 by 1 millimeter. So it's essentially around the size of a grain of rice. A cortical column contains many different neuron types that are organized into layers, and this layer organization is found all over the cortex, and the structure everywhere is remarkably similar. There are around 150,000 columns, and each column contains about 100,000 neurons and 500 million synapses. So understanding cortical columns is the key to understanding intelligence. Our implementation of learning modules maps nicely onto what we hypothesize happens in each cortical column based on the findings from neuroanatomy and physiology. So since learning modules are the key, let's get into the details of our latest evidence-based learning module. Sensor module via CMP, the cortical messaging protocol, sends displacement and features, poses, and attributes at locations to the learning module. That straw view is what learning module receives. Then the learning module outputs CMP to the motor system to perform movement. The basic loop happens each time step t. So the learning module receives displacement and features and poses and outputs motor movement. That's the basic learning module loop. Internally to the learning module, the displacement combined with features and poses at locations is enough information for the learning module to start to hypothesize whether the inputs correspond to any of the objects it already knows about. So the learning module assigns an object ID and pose to the series of displacements and features and poses at locations it receives. Basically, you're looking through a straw, and that sequence of movements tends to correspond to only one object that the learning module is guessing about, so it's going to identify that object. The object ID and object pose essentially summarize the stream of input received from a sensory module. Then the learning module via CMP sends the object pose and ID to a higher level module in the hierarchy. And also, while it is deciding what it is observing, the learning module sends and receives votes from its peer learning modules that allow it rapidly and as quickly as one shot to decide what object is being observed. And then lastly, to determine the motor output, the learning module comes up with a goal state, encodes it in CMP, and transmits it to the motor system. So to help visualize what is going on, here is a step-by-step animation of a single learning module going through the loop and recognizing between 4 different objects it knows about. The current hypotheses inside the learning module are depicted as point clouds on the bottom of the slide. The red points are accumulated evidence based on observed patch input and movement. And then once enough observations are gathered, we can see the evidence accumulate on a cup hypothesis. So on the upper left, you can see the path that the sensor is taking in space, looking at an object. The viewfinder is for your context, and what the sensor actually sees is the sensor patch in the center. Here's a similar example with a different object. In this case, the object is a die. Once again, the path through of the sensor looking at the object is in the upper left, and the bottom 4 images show what evidence was gathered, with red being more evidence and blue being less evidence. Here's a really cool one. So here's a visualization of how voting helps to rapidly decide on an object. Again, the viewfinder in the upper left corner is only for your context. The learning modules only see their corresponding patches. And so even though all patches see a different part of the object, across all 5 of them, there is a rapidly vanishing small number of objects that could match and explain the observation of each learning module. So this is the difference between you closing your eyes and trying to identify a cup with the tip of one finger versus grabbing the cup with your entire hand. Only the shape of the cup can explain the configuration and sensation of all of your fingers in that arrangement. And so because learning modules vote between themselves, they can rapidly recognize things because the input can only be explained by this one specific configuration of an object out of a huge number of what could be observed. This is what makes voting such a powerful mechanism. Lastly, a bit about the motor system and decision making. It is important to remember that every learning module is sensorimotor, in that every learning module, everywhere in the architecture, outputs motor projections. So they come from layer 5 over here. Now, you may have heard that of the motor cortex in the brain. However, neuroanatomically, every part of the neocortex outputs motor projections to the body, not just the motor cortex. So it is worth repeating, every learning module in the system outputs motor commands. As to what motor actions the learning module outputs, that is decided based on the state of the world and the policies active within the learning module. So we made the most progress on inference policies. We are working on learning policies, and manipulation policies are future work. We think of policies in two modes, model-free and model-based. A model-free policy does not involve the learning module. I enriched this diagram to include the CMP message from sensor module directly to the motor system. Neuroanatomically, model-free policies correspond to subcortical circuits. That is, you do not need the neocortex involved to execute a model-free policy. Here is an example of model-free policy. So, while this is neuroanatomically inspired, we can have generally helpful model-free policies. So we can have an if you fall off the objects, return to the object policy. And we can do that without involving any learning modules. This can be inside the sensor motor module and motor system loop. Similarly, we can have a policy that follows curves without involving the learning modules. If you think about how you touch things, you tend to follow the surfaces, and especially if you're trying to identify something, you're trying to trace contours and things like that. So there is enough data in the sensor module to follow curvature without models. As for model-based policies, these are the ones that leverage the models learned in the learning modules. So think about typing a word on a keyboard. Your learning modules send motor commands for words to appear, and then other learning modules tell fingers to move. And then some model-free policies execute the learn fine motor control movements required for familiar keystrokes. So a highlight here is that a model-based policy can recruit lower-level model-free policies for its work. And to highlight a model-free policy is like if you type on a keyboard, if somebody rearranged how the keyboard was, then you would become much slower because you can no longer delegate to model-free policies of where your subcortical circuits memorized what sequence of hand movements of the fingers you have to make to hit a specific key. You would then have to pay attention and look down and to hit specific keys, and that would make it much smaller, where you would no longer be able to use model-free policies. We also have some model-based policies that don't rely on explicit models. For example, guiding exploration to places on an object that will provide the most information to distinguish between current and most likely hypothesis. So we can test rotational symmetry. We can test object boundaries by expecting absence of object if we move off of it. And here is an example of a model-free and model-based policies in action together. We start off with a model-free exploration following an object curvature. Then to disambiguate, we use a model-based policy test to jump to a location where we will gather the most disambiguating data. So if you have a fork, a knife, and a spoon and touch the handle, then you may want to check the other end of the utensil to quickly determine which one of these it is. Okay, what can the system do today? So as mentioned briefly before, our current focus has been on object and pose recognition. Our experimental setups consist of learning and detecting objects at poses. We divide experiments into epochs, episodes, and steps and allow the system to learn and then match and update its learned objects. We maintain a list of benchmarks related to this research goal. And with that context, here's what the system can do. So it learns from very little data. You don't have to provide tons of images. Objects can be learned with a few data points. The system requires little to no supervision. It learns continuously without catastrophic forgetting. If it recognizes a known object, it can then switch to exploration mode and create a more detailed model to aid in future recognition. The system can recognize objects and their poses. The objects can have unseen before points, can be in novel orientations and locations, and can be noisy or partially obscured. We implemented sensors analogous to vision and touch, and the system demonstrates cross-modality transfer. That is, if we learn an object via our touch sensor, then we can recognize it with vision and vice versa. The system also generalizes based on object shapes. The model-free and model-based policies aid in more efficient learning and recognition. And lastly, the system uses significantly less compute than deep learning systems. So that's it. That's the high-level overview. There's a lot more to learn and understand, and you can find us at thousandbrains.org. We have a YouTube channel where we post lots of research meetings and lots of videos. So if this is of any interest, either now or in the future, I recommend like and subscribe, hit that bell. Uh, our code is MIT licensed and open source on GitHub, so you can find us at 1000 Brains Project. We have extensive documentation, so lots of reading if you're into reading things. We have a discourse forum where you can join us in conversation, ask, and discuss with others. And then we have also a reading list of papers and publications if this is of interest. Lastly, I will leave you with my favorite quote from the future. That Monty wasn't the first machine to see, but it was the first that learned to look and then to remember why. Thank you very much. And are there any questions?
Really nice, Tristan. Thank you so much. That was I learned even more than when I read the book because this is great because it's like now you're trying to put stuff into code and have real reference examples of just sort of the concepts that, at least I read about a couple of years ago. So that's it's great to see the progress. Yeah. Thank you.
I liked your approach of starting in the far distant future and then moving towards like today and kind of it's one of those like the throwing the rock in the lake and not realizing the impact of the ripples of the water, right? So I thought that was a really cool approach, Tristan.
Thanks. Glad that was entertaining.
Yeah. Questions, Tristan. I'm sure I have a lot, but for those who are here, anybody can come off mute right now, by the way. I turned all that off.
All right, I'll go. Quick question. So this was great. Thank you. Appreciate it. I did want to, I wonder, right? Are there other approaches that, because so many people are coming at this same sort of problem from so many different angles. Are there other methodologies or ways that other organizations, is there like what's the level of sharing that happens between, because right now everything is a research thing, this baby steps being taken by so many different groups. So generally speaking, I'm just trying to understand within this large ecosystem, is there a lot of sharing that happens? I see you guys are already a .org, so I'm sure you're sharing. But how much of it is like a collective thing that different people figure out different things, different projects figure out different things, and are then able to kind of build upon each other?
Okay, let me see. So the project just started officially on this year, like on January 1st. Is we kind of open sourced the code a little bit before then. So the um, the Thousand Brains project originally came from what was spun out of the company called Numenta, and So this was like 20 years, so like decades of research. Like this is a continuation of decades of research by lots of people that uh, has a through line through Numenta, and then now it became an open source nonprofit. So there is there is there are lots of published papers on the methods and things that are used here. So in the research arena, there's lots of peer-reviewed papers. There are more that are going to be published soon. I think there's some previews on archive, etc. So we are sharing just as everybody in the artificial intelligence field is sharing all our findings as soon as we can, as soon as we they are they meet muster, right? As far as sharing this particular sensory motor learning, there are there are people who are interested in doing more collaboration with us. So again, we just started in January, so things are just getting off the ground. It is still early. It's only been what, 5 months. Uh,
Okay.
but there are other people, like what I mentioned, for example, neuromorphic computing. There is, like, I'm aware of one lab at CMU that is implementing neuromorphic computing now in hardware that is based on a lot of concepts and the principles of the thousand brains theory, for example. So there is some, but this is not the prevailing view. So and also I'm not a researcher, so I'm not having those necessarily conversations with other researchers, right? Like I'm aware that our researchers are in meetings with others. Uh, as far as the open source code and the engineering that I can talk about, it's still very early on. It's a research project, but we're doing everything in the open and sharing as much as possible and looking for people to contribute. But that's
So can I ask
yeah.
a quick follow up? Based on what you are seeing from the engineering perspective, how objects are being identified and so on and so forth. When's the earliest you think we'll get a robot that can do the dishes?
But there is a reason I didn't put dates on that timeline. I don't know. But what I will say is, I guess I can bring the timeline up a little bit. Uh,
We should ask Boston Dynamics how close they are on getting that working, huh?
yeah, it's here we go. So we're saying, yeah, this one, right? So we can do object and pose recognition. Again, we're 5 months in, so this is a research project and it's also research code base. So I've been hired to make it to build out eventually a platform, an open source platform for people to be able to use. So we are still working towards that goal. So but these milestones they're very clear in all the researchers' minds. So what I mean by that is the researchers already have very good ideas about how compositional objects work and how the cortical column does. How to do object behaviors and world dynamics, very active area of research right now. And then we know that world manipulation and the other things will come after that. So the gap is there's theory development and what we know, and then making that work in software. We're gonna work on closing that gap, but I have no idea when it is. That's why this was sort of at best, like from product and applications perspective, this is more like a future talk. But this sequence, these are kind of the milestones to look out for. Like so, when if you follow the project, kind of just lurk, in the background and just see an update every now and then. When you see us talk about we're now implementing compositional objects, that's going to open up possibilities. If we have object behaviors and world dynamics, that's another kind of milestone and transition point. And this is, today, this is kind of, we think, the rough sequence will go, but research is research. No idea about the timeline. For what it's worth, I am very eager to make all of this reality as soon as possible. So, so we're working very hard, but no idea, I can tell you that we've been doing research. It's a research code base, and that's where we are today.
Hey, there's a
I see Ned has his hand raised. Thank you.
Yeah. Thank you for the presentation, Tristan, and thank you for all your contributions over the years. It's, as usual, quite interesting. May I ask how are you funded? I mean, what's given the state of the federal government right now, a lot of research is under threat. How were you funded for this Thousand Brains project?
We have funding from so Jeff Hawkins is funding the project, as well as the Gates Foundation. So Gates Foundation interest is, well, I've mentioned things. If you think Gates Foundation is very interested in in medical applications.
Of
So
course.
when I mentioned like an ultrasound that you can make more accessible to wider set of population without training mobile ultrasound, we just concluded a hackathon last week where one of our research teams they uh, they they implemented Monty telling you where to move an ultrasound in order to learn what's inside, like an ultrasound probe sort of thing. So those are the funding sources. Our team is small, and we're going to remain small. The philosophy there is that a small research team that can move quickly can get a lot done. We're not necessarily going to be the people that will commercialize any of this stuff. We are working in the open and hoping that others will be able to take advantage of what we're doing.
Thank you. Great model. Thank you.
Yeah, Tristan, maybe one more question. I'll throw one out there. I love how you started with the future, sort of our remember the future exercise, right? Like we love that as agilists, like usually to see like how things might go wrong. And I loved how you did it to see how things might go horribly, horribly right. It's like that's a great way to model. If you were to wind it back, when I think about LLMs were a research paper, but it was kind of Chat GPT was sort of the first killer app, or at least the one that we typically know about today. Might there be something like that that comes out in, I'm not saying a date or anything, but like that is based on what you're seeing from a software perspective and, even sort of the research, like it's like with a lot of irons in the fires and things moving fast, like anything could sort of spring up and then all of a sudden, boop, that's really just becomes part of our daily life. Is there anything you just mentioned the whole like, doing sort of medicine kind of applications? Is there anything that you might see that we would see first? And I know that world manipulation from the beginning of your talk is like not just a robot. It's like you could be all sorts of things that could be a quote unquote world. I don't know, like what might we see earlier or first or you know
Yeah, it's again, this is very difficult to predict the future.
yeah.
So the one thing that's very difficult to predict because we already we we are on the internet, technology, everything is technological, everything is text-based, etc. That will be like one thing I can say is that will be likely the last thing that happens.
Mm,
So it's just going to be this long thing that nobody, like it might end up being this thing that nobody pays attention to, and then eventually it will flip into much wider deployments. But uh, the we will I think I'm wildly speculating now, so other team members have probably different ideas. This is me going off the cuff here. With object pose recognition, the I don't know what the killer apps would be. The where I think it's useful, where my personal interests are taking me um, is this is gonna be an open source project, an open source platform that you can utilize that will object and pose recognition. They're kind of these universal problems that
mhm,
you might want to take in like your own local workshop. Any place where what's promising is any place where you do not have enough data to train like a traditional AI system, because they have to have lots and lots of data, right? Like a chat GPT was trained on all of human internet.
right.
Like so if you need to be trained not all on all of human internet, but you have a small data set of like, hey, in my workshop, show me where the things are, or in a warehouse, show me where the things are. Something around that where you have a custom situation, there's not a lot of data for a traditional AI system. that a killer app might emerge from that. So it becomes much more democratized, much more smaller scale, like individually for you specifically for some use case. Like that's the general hints that I'm thinking about and searching for.
Right.
But it all is dictated on which capabilities turn from research into production ready software. So
Yeah.
it's still very difficult right now, but it'll be, you know,
And the
yeah.
reason I'm asking is because if you have, this is a talk for, for the future and the present, and you have product folks and you have engineers that are products and product folks who are engineers, like that's like a hint of like, oh, if I was going to start learning about something, and you have it right there, it's like literally says object and pose recognition, but just some of those ideas that could spark some people to go off and sort of say, hey, I kind of do have this problem, or I've got object and pose in a sort of abstract format, and this could be, and I don't have a lot of training data, and I don't have this, but I do have this, I do have some of these sensors, and I could feed it in like that might be a good, interesting kind of practical way for folks to get started, even hobbyists and things like that. So that's why I was leading the question to like sort of like make it like sort of like relevant today, like where people might start. So
Well, so and that, I've been thinking a lot about this because this is a very future focused talk, and so like what will people get out of it today? One thing maybe to consider is if you've kind of seen the applications and kind of how the principles involved, etc., is maybe it's not necessarily this is what you can do with this system, but what to expect with existing systems.
right.
They're not going to be able to do that. So like, don't commit yourself to like, we're all going to solve this problem with this system. And if it's not working, there might be fundamental reasons for why it is not working.
Right.
And don't just burn all your resources being sold on like this, this is the approach that we all must do and we'll make it work. It's like you might make something work, but there are different approaches that are coming. I'm not saying I don't know when, you might not have, might not be able to afford waiting that long, but at least you're aware that there's maybe, the current approach is not what's going to fix all the problems that you have today.
Right. Just like the approaches of the past that were largely generated in much more inefficient ways. You could say, like, we keep making it better and better through these different kind of approaches to solve problems. So yeah, this is, if nothing else, like the mental model of thinking beyond where we are today and asking questions about, well, could we do it a different way? I think is, to your point, is very good. Whenever if you're in product management or engineering, it's kind of like, yes, you could spin up 10 million servers and use this algorithmic approach, or you could, do something much simpler with a different kind of algorithm. Yeah, maybe last question from Munzer.
So my name is Manzar. I'm in Dallas, Texas area. This is my first time here.
Oh,
I
great.
use chat. Yeah, my background is computer science, finance, philosophy, artificial intelligence, etc., etc. I'm an older guy. Uh, so I do use ChatGPT a lot, many which way, even in legal matter and AI development and other things. And it's very helpful in many different areas, no doubt in that. But, big but, when I ask a real critical thinking question, it fails so miserably. I could not believe it. They even call it AI. From my point of view, I could be wrong. You folks are the experts, but it has no sign of real intelligence. It has a skill set like a robot. They are very good uh, in General Motor automated manufacturing plant. It can do electric welding in the speed and accuracy. No human being can match that. And I use ChatGPT. But critical question which is designed to test the intelligence, creativity, independent thinking. I have done that over and over again. Every single time ChatGPT did not only fail, and it's not only ChatGPT. I have used about 6 different platform application that's available. It fails so miserably, and then after 1 hour talking to it, it realized its mistake, it admits, but it can't remember next time. At the same time, when I call my son, adult son in California from Stanford University, ask him to ask the chat GPT the same question because he's entering from different IP address, other thing. Chat GPT did not learn anything from me, which he admitted he was wrong, but it still keeps giving the wrong answer. I don't understand why it is. I would like to hear your opinion about it. Thank you.
Thanks for the question, Mansur. Tristan, do you have some thoughts on that one?
Thank you. So interestingly enough, I avoided a lot of LLMs and deep learning because I was very focused on how the human intelligence works. So I can't tell you why you are seeing the results you are seeing. What I think will happen with the 1,000 brain systems is that sort of awareness and context and that you're describing, I think we'll be capable of that, but that will come towards the end of the abstraction, multi-agent system, that sort of thing. And the hints maybe and as an answer to your question is, what we think is a prerequisite to that, and that is the real world grounded understanding. So when you tell ChatGPT bird, it has all the content of the internet to imply what a bird is, but it never itself saw a bird. It didn't observe birds. It didn't hear birds. It didn't do any of that. And so that grounded real world understanding, we believe, is essential to making an intelligent system. That's how our brains work. And so that might be why you're seeing the results you're seeing, but that's also why we think it'll come last. And we have to have a path to have useful systems go all the way up to that point so that we do get a chance to make an intelligent system in the end.
Right. One thing that Mansur,
Go.
there's a talk that John Hines gave us last year. It's on our YouTube channel. You can reach out to me. I can point you to it. But it was called Explaining Explainability, and it really talks specifically about how LLMs work and what problems there are versus different kinds of neural networks and things like that. There's even a book that's like it's got the word Y in it. It's not start with Y. It's another one anyway. But it's really a like sort of a semi rant from one of the researchers in the field that talks about like this is not LLMs are not the way to go because they you can't explain what they're doing exactly to your point. They don't understand. And this model, one of the things that really appealed to me when I was reading the book a couple of years ago was it sort of made sense to Tristan's point. Like this is how humans learn. This is how we do it through interacting with the world, and that is what learning is. And it seemed like a really interesting approach for.
Of course, if you ask me how I reasoned my way to something, I'll give you a bullshit story. Because I really don't know how I got what I got that insight in the shower or something. If you ask me for an explanation, I'll make something up, and I
Right.
expect that AIs will be able to do that too.
Indeed, indeed. Well, we're now if our fearless leader Max Akizu is here, we would say we start on time, we end on time. We didn't quite start on time, and we've gone long today, and it was worth it because Max slides. Because this was just a fascinating talk, Tristan. Thank you so much for your time and contribution here. Really appreciate it. Once again, like Ned said, your ongoing contribution to Agile Austin for decade or decades. We lose track after so many years. And thanks everybody for being here. Like it really, the fact that you were here made this. This will be on the recording out in the real world. And yeah, I'll.
Thanks, Tristan. Appreciate it.
Thank you
Thanks,
so much.
everyone.
It's good to see everybody.
Thanks,
Bye, Chris.
everybody. Good to see you. Cheers.